Uh-huh. also to its next. That way I can get set up for the next iteration of the algorithm. At this point, I need to increment my count by 1. So now count is 1. Since my count is odd, I should take a node from list 1. So I look at my current 1 pointer, and I add b to the tail, just like this. And I make progress on all of my variables, right? So I'm going to progress current 1, I'm going to progress my tail, and increment my count to 2. Since it's even, now I should take a node from list 2. So I take my r from current 2. And when I set current 2 to its next, it's going to become null. When I set tail to its next, it's going to be set to the r. And then I increment my count, so now my count is 3. And now I have an important scenario. It looks like I've exhausted all of the nodes in list 2. We spoke about this scenario, right? Whenever we finish all of the nodes of one of our lists, we should just terminate our output with all of the remaining nodes of our other list, the non-empty list. And so at this point, what I can do is just take my current one, basically this C chain and everything after it, and just put it after the tail in my output.
Tail.next. If current 1, if not current 1, then tail.next equal to current 2. If not current 2, then tail.next equal to current 1. I think that's what I would want. Tail is going to be moved all the way down to tail. Go down. So adjust tail. Delete all this other stuff. Tail is here. Delete this other stuff. Tail is here. This other stuff. Tail is here. Two. 3. Shouldn't there be one more? No. Start out with tail here. And then we move this one on count is equal to 0. And we set tail dot next to current 2. After we when it's all said and done, we move that next. And then we set B and we move that there. And then we set Y and then we move that there. And then we set C. And then we loop around and it's done. However, we take this right here, current 2 is not done. Or so current 1 is done. So we set the next to current 2. So we take this and put it here. Yeah, I guess that's it. Set like a head 1 is equal to current 1 is equal to head 1. 2 is equal to head 2. Tail is equal to head. Current 1 is equal to head 1 dot. Let's do tail. The head 1, current 1. Is equal to head dot next. Something like that.
Just like this. And of course, I want to complete the connection over here. And this would actually be the correct output. And so overall, our strategy was to maintain pointers to both of our respective linked lists and maintain a count, right? Depending on whether the count is even or odd, then that'll tell me from which list I should take my next node. And along with that, we also need to maintain some tail pointer we can use so we can actually build up the linked list output. Let's talk about the complexity of this one. Since we have 2 linked lists as input into this problem, we should probably use 2 terms to describe its complexity. So if I say n is the length of list 1 and I say m is the length of list 2, then I can say the time complexity is the minimum between n and m. Recall that when we just stepped through this algorithm, we really only needed as many iterations as the shorter linked list. Recall the algorithm we just traced through. Once we hit the end of one of our linked lists, we know we just finished the algorithm by taking the remaining nodes of the other list and just tack it on to the end. And that finishing step only takes O of 1 time. So really, as soon as one of our linked lists runs out, which will always be, in general, the shorter one, then I can just finish my algorithm. I actually don't have to iterate fully through both of them. And I would still consider this technically, some form of a linear runtime. For the space complexity, we can say that the space here is just constant, right? We're not actually creating any new nodes. We're simply rerouting all of these next pointers. And in terms of our variables, we only use a fixed number of them. And so overall, this seems like a reasonable strategy. What I want you to do is try to code up this one on your own. It's going to be some really interesting code, a new pattern.
So let's see. Again, we have head 1 and head 2. And what we want to do is take head 1. I want to set current 1 is equal to, let's to current 1 like that is equal to head 1. Current 2 is equal to head 2. And we want the tail tail is equal to head 1. Current is equal to head 1 dot next. And then we want to say while current 1 and current 2, while they're true, we want to say if the we also want an account variable is equal to 0 if count divided by or modulo 2 is equal to 0, then it's even, and we want it to shift, or we want to set tail dot next equal to current 2, and we want to shift current 2 2 is equal to current 2 dot next, and else we want tail dot next equal to current 1. We want current 1 equal to current 1 dot next. Shift it forward, and we always want to move tail to the next spot. And then so if the loop is broken, if current is not, if current is null, then what we want to do is current is null, then we're sending current 1 dot next equal to the current position of current 2, and the opposite with current 2 dot next equal to current 1. So that should move the rest over, and then do we just return the tail? Return the tail. Or how does that work? I don't know how that
Pattern
works.
for us, that is. This here is just algorithm we should probably here. And this would actually be the correct output. And so overall, our strategy was to maintain pointers.
I don't know how this works. Because the tail is shifted all the way. Oh, it says do this in place by mutating the original nodes. I mean, that's what I'm doing, right? to return head 1. Test. This should be current 2 dot next. No. Current 1 is equal to current 2, not dot next. Current 1 is equal to current 2. Current 2 is equal to current 1. Expected this and got YZ. I'm not iterating the counter at the end. Count plus or equal to 1. A little bit closer now. A little bit closer now. ABC. The thing is, if I set, let me see, print current. So I think I should get into here where current 1 is equal to current 2. You say print current 2. Current 1 is current 1 is equal to current 2 is equal to Z. So it's already Z. It is already Z. But don't I want that? I already have C. Don't I want Z? I need C to point to Z. But if C is already here, how does it point? That's the problem. I mean, C is here though. Doesn't it just... Current 1 is Z. I don't know how to do that.
Maintain pointers, just like this. And of course, I want to complete the connection over here.
Tail. Oh. It's tail.next. Tail.next is equal to current 2 and tail.next. It's equal to... There we go. So this would be the is. Let's remove this. What am I going recommend for sandboxing while execute file as is without injecting any test. No, I meant to do this. Fill in X count plus equal to 1. All right. Let's see what he said.
Hey programmers, Alvin here. Right now, let's go over a Python solution for the zipper list problem. So do make sure you've watched the approach video because we're going to implement that strategy right now. So we'll start by setting up a few pointers. So some foundational code we'll need is set some current 1 pointer to head 1, and likewise for head 2. Pretty classic pattern by now. And when we write this while loop, we want to really loop while both are not none, right? So while current 1 is not none, and current 2 is not none. Really just combining traversal for both linked lists simultaneously. So it's looking pretty good. When we talk about the true logic for this problem, we do want to merge or just zipper these linked lists together. And we should always start with the first node of list 1, right? So for this example, I'm given ABC and XYZ. I always start with A, right? And so I'll work that into my code over here. So we still have to do this while loop. But let's set up our way to construct the output, right? We're not creating any new nodes, but we do have to reassign the next pointers of the existing nodes, right? So what I can do is set up some, we'll say, tail. And I know that the tail should begin at head 1. So this will give me a way where I can just keep adding my new nodes into the tail, right? And by the end, I know I need to just return head 1 because I'm mutating this entire list. And so this is looking pretty good. And now I just need to make sure I update all of these pointers appropriately, right? So let's talk about how we're going to alternate. So a way to get the alternating pattern, like we spoke about in the approach, is just use a count number. So I'll set equal to 0, and then just check whether it's even or odd, right? So something like this, right? If count, we'll say mod 2, if it's even, do one thing. Otherwise, it's odd, do something else. Since I'm always starting my linked list with the node from head 1, then I need to make sure that I actually progress this. So current 1 should really just start afterwards. Right, so I'm going to assume that head 1 is already part of my linked list, right? Tail is pointing to the output list over here. And for my counter, because I already took something from list 1, then I guess if my count is even, I'm going to take a node from list 2. When it's odd, I'll take a node from list 1. So let's start to code that up. So what I can do is set tail.next, and I'll set it equal to current 2, right? So I'm consuming a node from list 2, right? And what I want to do is also progress current 2. So I can say current 2 equals current 2.next. This is a really important step because if you don't update the pointer for current 2 and make it move rightward, then you're going to be like reusing nodes, which is bad, right? And then this would be pretty symmetric for the else case. Otherwise, we have an odd count. So take a node from list 1. Nice. And in either scenario, I always need to move my tail. Right? The tail just helps me construct the linked list. So I'll say tail equal tail.next. And also be sure to increment your count. So count plus equals 1. That way you can keep alternating. So that's looking pretty good. One thing we do have to be concerned with, like we said in the approach, is what if one of your lists ends early, right? If you finish one of your lists, then you just tack on the elements of the other list. So as soon as one of my current pointers is none, I would exit this while loop. I need to check for any leftovers, so I'll check maybe over here. If current 1 is not none, that means there's some leftovers on current 1. Just take my tails next and make that point to those remaining elements. And I should new line this. That'll be the same thing for current 2. So if there are some remaining stuff in current 1, then just stack them on at the tail. Likewise for current 2. And this, of course, is outside of the while loop, just some finishing code. All right, let's go ahead and give this a test run. It's not too long of some code, but it is a fairly new pattern for us, so it's okay if you find this a little difficult. We'll practice this pattern a lot, I promise. Awesome, so this code is working. Like we said, this is going to be a linear time and constant space. New pattern for us, so it's okay if you find this or this. So we'll kind of redefine it up top for zipper lists. Pretty different strategy. I think for our recursive version, we don't really need to use like a count to alternate. So what I'll start with is some base cases, right? So if I hit the ends of my linked list, so let's say if head 1 is none and head 2 is none, then I'm totally done. So just return the zippered version of that, right? If head 1 is none, head 2 is none, those are two empty lists, right? To zipper them together, just return the empty list. Nice. But what if only one of them is none? So afterwards, what if head 1 is the only one that's none? So that means that head 2 still has stuff. So I have some remaining things on head 2, so just return head 2, right? This base case is similar to the finishing code we did over here. Right, how can we kind of just take all the remaining nodes of the other list when one of them empties out? I'll make it symmetric for the right-hand side. Head 2 is empty, then just return head 1. Nice. And so what I need to be sure to do is this zipper list function needs to always return a node, right? A node that represents like the head of that remaining list. So now comes my recursive part, right? So I need to alternate between these nodes. So what I could say is, all right, head 1 next definitely needs to point to head 2. That's how you actually start alternating, right? And I need to do a recursive call eventually. And as soon as I do this line, I kind of just overwrote head 1's original next. So I'd lose access to that. So I should probably save it up front. So very common linked list thing, right? You have to save some pointers before you just clobber them. So I'll call this next 1. I think while we're here, let's do the same thing for next 2. Kind of like the symmetry of that. So I make head 1's next point to head 2. Awesome. And then from there, head 2, that next, needs to be set to whatever the recursive call is of zipper lists, right? So here I do my recursion, say zipper lists of next 1 and next 2, right? So again, what we have to do is assume that this function is working. So I should get back the head of the zippered list for the rest of the things, right? Next 1, next 2. And then I need to complete a return here. So right now, in the recursive case, this function doesn't return anything. So it needs to return its head, which I said should be head 1 here. And this should just apply recursively. So here's what we'll do. Let us trace through this a little bit. So I'm going to steal maybe this linked list over here. Do a little ASCII art action. And hopefully as you also, come up with your own solutions and all that jazz, to me, you should be kind of somewhat drawing it. So drawing a whiteboard, drawing some ASCII art, find a way to visualize these. To me, if you can't visualize it, then maybe you can't really write the code for it either. Because usually drawing it is a lot easier than the code in the first place, right? And so here's how this recursive algorithm works. So we know at the start we're going to be given head 1, head 2. So maybe I'll just lay down those pointers visually. So call this one H1, this one H2, like that. And we know that we don't have a base case that's going to fire right now because I have 2 nodes. So I don't run this code. What I do is save some references to the next of both of them. So I'll just label that as N1, so next 1, and next 2, just so I don't lose any references. And the really important part is I set head 1's not next. I'm going to change head 1's arrow to point to head 2. So what does that look like? So although I'm just rewiring these next pointers, I'm not creating any new nodes, just visually I'm just going to duplicate down here. I would be saying that head 1, which is A, its next should become head 2, X. Awesome. And then from there I'm saying head 2's next, so X's next should be the result of zipper lists on next 1, next 2. And here's where you have to do like your recursive leap of faith, right? When I make this zipper list call, what I am going to do is kind of ignore these anymore. So I just finished evaluating some of that. And now B is head 1 and Y is head 2, right? And whatever that call returns, I would put exactly here, right? So if we kind of step through one more stack frame of this, I take head 1's next, so B, and point it to head 2, right? Head 1 next point to head 2. So B points to Y, and so on. And what's really important about that is not only do I point B to Y, but I return B back to the parent, right? So that would actually form the correct chain of AX, BY, and so on. Cool, so let's give this a test run, see what we get. I think there's always a value to solving problems in a few different ways. It's okay to pick a favorite, but challenge yourself. Nice, and there we have it. All right, programmers, so that's all I got for this zipper list problem. I want you to practice both of these, and I'll catch you in the next one. See you there.
Hmm. So recursively, how does this work? Let's say we get down to head 1 is none and head 2 is none. Return none. head 1 is none, only return head 2. Head 2 is 1 only, return head 1. Qué tontos, qué locos somos tú y yo. Estando con otros y pensando no. And then this right here, going back in with the next 2 nodes. And you're, what are you doing with them? You're pointing them to each other. You're saying head 1 dot next. Starting from the very beginning. So recursively, recursive solution, we have this right here. And we say start with head 1, head 2, we put it in there, and we say the arrow, we set next 1 and next 2, and then we set head 1 dot next to head 2, and then we go into the recursion. So we have head 1, head 2. Next. Next 1 and next 2. So every time we move head1.next to head2. Right? And we shift the pointers. We move head.1 next to head2. Because this would be the new head1 and the new head2. New head1 and then new head2. And you would set head1.next equal to head2 and head2.next. 2.next points to this next iteration, which is going to return head1 pretty much what's happening. This one goes here. One goes here. Here. Goes here. This goes here, and this goes here. Before I do that, these move like this. And then these go boom, and then these move. Head1, head2. And then goes back up the recursion call. Connecting. So this stuff happens up the recursion call, this one right here. Recursive call, recursive call, recursive call, until you're there and you return that head node. Okay. So let's go to the next section. See binary tree. Actually, I wanted to check this real quick.
Hey programmers, Alvin here. I just wanted to interrupt the regularly scheduled programming to reorient ourselves on the big picture, right? So right now we're working through some really cool graph problems, and I know what you're thinking, right? I'm throwing a lot of new concepts right at you. In the last module, we covered a lot of binary tree problems, and you're probably feeling that, as soon as you're getting comfortable with binary trees, I switch it up on you and then throw graphs right in your face, which is, actually the case. However, do bear in mind that, as we're covering these brand new topics and concepts in the graph topic, it is affirming your knowledge in binary trees. And of course, the thing you need to study is probably the thing you're uncomfortable with. And so if you're feeling like these graph problems are giving you a hard time, don't worry, right? Feel free to review, the previous graph problems, and then you'll get the same mastery that you did in the previous binary tree section, right? We're going to keep increasing difficulty as we move further along in the course, especially when we attack a brand new topic. So keep doing what you're doing, and I'll see you in the next one.
Let's see what that would entail.
Hey programmers, welcome to our module on binary trees. In this module, I'm going to show you the basic binary tree algorithms, that is the depth first traversal, the breadth first traversal, and we're going to utilize just these two algorithms to solve a ton of different and diverse binary tree problems. I'll see you there.
Okay. +10.
So first order of business is, let's actually understand what the word tree even means in like the programming concept, right? So when we visualize a tree contains many nodes. Typically we draw nodes as circles, right? And these nodes can also point to other nodes. So here I have one node, and it could point to some other node, right? And it could point to any number of nodes. So here the circles, I'm going to refer to them as nodes, and the lines or arrows between them, I'm going to call edges, right? And so this is an example of a tree. And trees can, of course, come in many different shapes and sizes. So here's quite a large tree. Let's try to understand a few terms we can use during our technical interviews. And this is something I highly recommend, right? Helps if you speak the language. It does show that you have proficiency dealing with the data structure. We could store values within the nodes of our tree. For now, I'm just going to put some letters. When it comes to your programs, you can store any type you want. You can store integers, numbers, or even other objects. So because we have a tree, we like to use familial relationships. In other words, I think of like a family tree, right? So if I look at node B, let's say I call them the parent. If B is the parent, I know the children of B are just the D and E nodes, right? Parent and child is like a relative relationship. Let's say I kind of change my frame of reference, and let's say I looked at A as the parent. Well, in that scenario, then B and C are the children of A, right? For the case of the C node, if I think of C as a parent, it only has one child, its lone child being the F node. So feel free to use that parent-child relationship when describing the relationship among nodes within a tree. Another term we'll use a lot in the context of trees is the word root, right? So a root is going to be a node that has no parent. So in this tree, A is the root, because A has no parent, right? There are no arrows going into the A node. On the flip side of that, if I look at the nodes D, E, and F, we call them leaf nodes. A leaf node is a node that has no children, right? So D and F have no outgoing arrows. Typically in a binary tree, we're going to have a single root, and we could have many leaves. One thing I want to be sure to do is make sure you generalize your understanding of a leaf, right? So in this particular example, looks like every leaf is 2 edges away from the root, counting the number of arrows from the root to any leaf. It could be the case that my leaves occur at different levels, right? So I removed that F node, in which case C is now a leaf, right? Although a C is on like a different level than D and E, it's not at the bottommost level, it is the case that it's still a leaf, right? A leaf node is just a node that has 0 children. All right, so with all of those terms out of the way, now let's hone in on the real topic here, right? I talked a lot about trees, but really in this course, I want to go over the basics of binary trees, right? So let's look at that binary part to begin with. That's really a dead giveaway. We know binary has to do with the number 2. A binary tree is a tree where every node has at most 2 children, right? So currently on the screen, I have a binary tree. If I gave A another child, let's say a third node over here of F, this would be a tree, but not a binary tree, right? It would be like a ternary tree because I have at most 3 children. So let's say I kind of remove that extra node. Now it's back to a binary tree. And it could be the case that a node has less than 2 children, but still be a binary tree, right? So if I gave C just a child of F, this is still a binary tree. So if I look at any node within my tree, that node will have 0, 1, or 2 children, and no one has more than 2 children, right? So you want to be sure to remember that a node in a binary tree could have less than 2 children. All right, so that'll be the first criteria for understanding what a binary tree is, right? It's probably the easiest criteria. At most, 2 children per node. What we'll also want to be sure to add into our definition, have a robust understanding, is to also remember that, at least for us in computer science, we think of our binary trees as having exactly one root, meaning there should be only a single node that has no parent, right? Typically when we draw it, it would be like the topmost node. So right now, this is definitely, so far, a binary tree. If I had some other node in this drawing, like G, right? G also has no parents, I would no longer consider this a classic binary tree, right? So watch out for that. Let's go on to our final criteria.
Exactly.
We also need one more ingredient, and that's exactly one path between the root and any node, right? So looking at my example to the left, this is indeed a binary tree that meets all 3 criteria. Now let's say I chose the root and any node. Obviously there's only one root, so we're definitely considering the A node. Let's say I chose some random node like E. If this is really a binary tree, then we're guaranteed to have only a single path that connects A to E. A path is really just a series of connected nodes I can travel through, right? So to get from the root A to the node E, I can go from A to B to E, and that would be one path. And that's the only way to get from A to E. That's what I mean by exactly one path. Let's say I chose another node like F. There is also exactly one way to get from the root to F, and that's just ACF. That would be the only path. If I added some additional connections or edges within my tree, I can get a scenario like this. This would no longer be a binary tree. For one, we can see that B has 3 children, but also does not have a unique path between the root and any node. For example, if I chose the root of A and the node of F, one way to get there is by going ACF, but another way to get there would be ABCF, right? And so do watch out for all 3 criteria when you're considering a binary tree. Awesome. So let's look at some smaller examples, and this is where I think some students tend to struggle with their understanding of binary trees. So if I took out some nodes over here, this would definitely still be a binary tree, right? Just looking at our different rules, right? Let's say the root node A only had 1 child, it would still be a binary tree, right? Because the binary tree only demands that we have at most 2 children. We still have 1 root, and we still have only 1 path from root to any node. Let's say I have the smallest tree that has a node, which would be the singleton tree. This is still considered a binary tree, right? It has 1 root. There's not really any paths to be had here except the root to itself, and every node does have at most 2 children. Here we have 0 children, right? The final edge case I want to think about is what happens when we have no nodes, right? We consider this as the empty tree. This is a very special case, and we should consider any empty tree as actually being a binary tree. That's going to be very useful when we come up with some algorithms later on, right? So a common edge case I have to consider is what happens when we have an empty tree. And that's a tree with 0 nodes, right? Let's look at another example. Let's say I had this structure. So take a moment, look at it, and see if this meets our criteria. This would not be considered a binary tree. So if you look at your different criteria, now looking at the first one, it does have at most 2 children per node, so that's okay. But we can't identify exactly 1 root here. Remember that a root node is a node that has no parent, right? If you look at every node in this picture, every node has exactly 1 ingoing arrow. So that means every node has at least 1 parent, right? So it doesn't meet that criteria. And furthermore, there is not exactly 1 path between the root and any node because we have a cycle within the structure. So for example, let's say I was starting at A, right? And I wanted to travel to C. One way to get there would be to go A, B, C. That would be 1 path, but I could also have another path where I just go around twice and go A, B, C again. There would actually be an infinite number of paths in this scenario. Because of that, this is definitely not a binary tree, and there are kind of many reasons for that. If I had a different example, looking at this one, now I meet criteria 1 and 2, right? I have at most 2 children for every node, but I also still have exactly 1 root node. Here I would consider Z the root node. However, there is not 1 path between the root and any node, and because I have that cycle. So these rules are really worth remembering. They're really going to help you solve much more difficult binary tree problems. And if you remember these 3 rules, you can identify different problems in a binary tree framework. In other words, the hardest problems that you'll encounter in your interviews are problems where they don't tell you straight up what data structure you're dealing with. You're just going to have to notice the pattern. In other words, what if I gave you some structure like this? Take a moment and figure out if this is a binary tree. If you look closely, this does meet all of the 3 criteria to be a binary tree. I can just treat A as the root because it has no parent, and I can treat nodes D, E, and F as the leaves because they have no children. I just drew this in a pretty interesting way, right? If you rearrange things in a classical binary tree sense, it would look like this. More importantly, this has the same relationships as a previous drawing. I just drew it in a top-down fashion, right? So no matter what, do understand these 3 rules for a binary tree, right? Because sometimes it may not be as explicit as a nice triangular shaped drawing. Awesome. So we talked a lot about the theory of how to look at and reason through some binary tree definitions. Let's go ahead and start to talk about how we could represent a binary tree programmatically. In other words, how can we do this in some code? Well, no matter your programming language of choice, I think you're going to represent these as objects. In other words, every node here is going to be some object. So it could be like an instance of a class. The properties we want to store now within this object would be the current value. So I need something to store like the A of my current node, but I also need to refer to some children. So I will also need some left and right pointers to the children, right? Those are just going to be some properties on that object. In a classic binary tree, it is very common to refer to the 2 children using a left and right direction. Notice that some nodes here, like the C node, they're only going to have 1 child, right? C only has a node.right. It does not have a left. So we're going to have to use some empty value like null or undefined to represent a child that doesn't exist, right? Especially for a node like E, E has no left and also no right. So here's what we'll do. Let's go ahead and hop into my text editor, and I'll show you how you could represent a binary tree programmatically.
All right.
Hey programmers, Alvin here. Right now I want to do a little Python warm-up for our upcoming binary tree problems. All I want to do in this video is show you how you could create a pretty classic binary tree node class. Then I'll show you how to wire up a quick and dirty binary tree. That way you can start testing your algorithms, right? So I'm going to create a node class. And when it comes to what I need to store inside of this node, I'm going to need 3 properties overall. So in the initialize method, I'm going to take in self as always, just classic Python stuff here. I'm also going to take in some initial value, right? So this value can store any type. I just want to start by saying self.val equals the val I'm passed in, right? So far this looks exactly like a node class for a linked list, right? But then I need 2 additional properties here. I'm going to store a reference to the left child of this binary tree node. I'll default it to none. I'm going to set its right child to also be none. So notice that this node can have up to 2 children, right? Left and right. And when it comes to creating some nodes, it's pretty straightforward. I can say I have a variable A. I'm going to create a node, store the value of the string A over here, right? Let's say I just stored lowercase characters. Create a few different nodes. Nothing too fancy here. So I have B, C, D, E, and for good measure, let's also do an F here. You're gonna see me create this tree many times during the course. So this creates a bunch of like disconnected binary tree nodes, but if I want to connect them together, I need to set left and right. So let's say I made A's left, the B node, I made A's right, the C node, then B's left, the D node, B's right, the E node, and finally I think C's right is going to be the F node, right? And so this would have the effect of forming a pretty cool binary tree with this shape. I know I have A as the root, so A's over here. It has a left and right child, where the left child is B and the right child is C, right? And if I look at that B node, that has a left of D and a right of E. So I look something like this, right? D, E. And then finally, C just has a right node of F. Notice that C does not have a left child, so its left remains as none, which is totally fine. Right? And the reason that I'm going to use this tree a lot in our upcoming binary tree problems is it's sufficiently large, right? It has a few different nodes, but it also has some diverse nodes, right? I have a node like A, which has 2 children. I have a node like C that has just 1 child. Of course, I have nodes or leaves like D and F that have 0 children, right? So if you're on like an interview, or if you're kind of trying to explore, debug, and trace through your code, you want to have a fairly large example, but not too large that it's like a pain to actually trace through. But you also want some diverse cases of nodes within your example. So in the next few tasks, I'm going to flip it over to you, and we'll walk through and approach some cool binary tree algorithms together.
Write a function, depth first values, that takes in the root of a binary tree. The function should return a list containing all of the values of the tree in depth first order. Hey, this is our first binary tree problem, so you should be liberal with watching the approach and walkthrough. Be productive, not stubborn. Yeah. So write a function, depth first values, that takes in the root in the binary tree. The function should return a list containing all the values at the depth first. And the values of the tree in depth first order. So A, B, D, E, C, F. So the base case is if the root is equal to none, if the root is none, then return a list retaining all the values of the tree in depth first order. If let's see if we can draw it. Down, 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 Write a function depth first for values that takes in the root of the binary tree. The function should return a list containing all the values in depth first order. So, I want to start at the root, which is A. Start at the root. And we go down. And we go down. And then we return D. Maybe return an empty list at the end. It's like when you go down to null. Like you go down to null. Right? But here, so we go down to null. A, B, D down to null. And when we return from null, we're returning a empty list, right? And we can return here another we can go, we actually have a node here. Or no, we don't. Like, I don't know if we just like keep doing that. Before we even, if we do left and it returns empty list. Right, returns empty. Let me just append it. Let's see, chat. AI append. want to know how to concatenate two lists. You could do plus or extend. So let's keep drawing this out. So we have this goes to another circle. That's E. And E has these two things, just like this. And then we have and so thing is I want to also append these two. In depth first order. Go D. Go down D. Or no, we append up here. A. B. D. E. C. F. So we append on the way down. Before we go in, we append. Before we return, we're returning an array. Let's see how it does it.
Hey programmers, Alvin here. Right now I want to go over this depth first values problem. So this will be a good review of the depth first traversal algorithm. So what do we want to do in this problem? Well, what we want to do is take in a binary tree. In particular, your function is going to take in the root of the binary tree. And just recall that given the root node of a binary tree, we know that that node is going to have pointers to its left and right children, which may point to other nodes. However, if let's say a node does not have a left or right child, then its pointer is going to be set to null. So that's how we'll represent our binary tree programmatically. But for now, let's just stick to the visual representation of our tree. So for our depth first traversal, we could start with the root node of A. What we'll do is we'll just add that to some collection. And we're going to have to maintain these in a very particular order. Then from there, according to a depth first traversal, I could go to B. And here's where we make our really important decision, right? We can either go to C or D. If I'm doing a depth first traversal, I need to go deeper in the tree before I move laterally. So that means I go from B to D. And once I bottom out at D, there's nowhere deeper I can go from D. And so now I move laterally to the E node. And this pattern continues, right? I don't have anything deeper from E, so now I go to C. And then from C, I go to F. So this would be a depth first traversal on this binary tree. Notice that it goes A, B, D, E, C, F. And again, the really important characteristic is we must go deeper in the tree until we can't anymore, and then we can go across the tree. That being said, how can we actually manage to implement this algorithm? If you're familiar with depth first traditionally, then we know that it's going to use a data structure like a stack. So let's get situated over here. So we'll trace through that again, but this time taking a really close look at how we can use a stack to accomplish that direct order.
Okay.
And so just recall that a stack is a sequential data structure where we can only add things to the top of the stack and remove things from the top of the stack. So a really important characteristic is we can't really insert or remove elements from anywhere but the top of the stack. So when I add things to the stack, I always add to the top like this. When I remove things, it's also from the top like this. All right, so when I begin this depth first traversal algorithm, I'm going to start with the root node of A. And by default, I really just take that root node and I just store it on my stack. So it's the only thing on my stack right now. I'll use these rectangles to represent my different stack frames. And really in my program, that would just mean storing the actual instance of node or some pointer to it. Cool. And then from there, I actually begin my main algorithm. So the main flow of a depth first reversal will check if the stack is empty. Right now the stack is not empty because I have at least one element. And so what I do is I start by removing or popping the top element of my stack. So I'm going to remove the A, and I'll label that as my current node being explored. And when something leaves the stack, then I can consider it being visited right now. So I need to list out my values because that's the whole point of this problem, right? So by now I've just visited the A node. At this point, I can look at that node's children now. So I look at the A node in the tree, and I see that it has a B child on its left and a C child on its right. And from there, I push or add those two children to my stack. So I'm going to put C first, and I put B afterwards. And notice if I push my right child first, followed by my left child, that makes it such that my left child is at the top of my stack, which means that I would hit them next. And that actually ends my first iteration of this depth first reversal. And now I ask that same question. Is my stack...
So we want to look at a stack. And we want to say, okay, we have boom. So the first thing is A. And then we have values A. Our values is nothing. And then we pop off the stack. And then we go values A. After it's pop off the stack. And then the next thing is C and B. This is C A dot left, A dot right. A dot left. And then we pop off the thing from the stack, pop off this from the stack, add B here. And once we have that, we reach the null values. And for null values, we don't do anything.
stack empty? It's not, so I remove the top of my stack. I'll call B my current, which means I can print it out or insert it into my values list. Nice. From there, I consider B's children. B has two children, so I add them both. I push E, followed by pushing D. That ends that iteration.
Oh, wait. D and E. D is left. No. E is right, so we gotta put E here and D here. So B left, B right, and B left. Nope. Here.
Now something interesting happens. My stack is still not empty, so I know I removed the top, so I call D my current. I add D to my list of values, but if I look at D's children, it actually has no children, right? And so there's nothing to add to the stack from here. And so technically I finished this iteration. And now I still have stuff on my stack, so now I pop E off the top of my stack. Same thing as before.
Okay. So then we do it again. With D popped off. With E popped off. And then on C side, do we add on? Pop off E, add on. What do we add on? Add on F. And F is C, right? C, right. And then the next one is pop off F. A, B, C. Oh, no, no. We pop off C. Yeah, we gotta, before we do this, we popped off E to add it. And then the next thing we do is pop off C to add it. And then we add F. Pop off C and you add F. Pop off C and you add F. Right? Pop it off. So it's C. F. And then you pop off F and you add it. And it's not going to have any children. And then you're done.
So in this problem, it's before, right? I add E to my values. E has no children, so I'm done with that iteration. Finally, I have C. I remove C from the stack, and I print it out in my values. And then at this point, I see that the C node only has one child. So I'm just going to push the children that exist. So I would push the F node onto my stack. And that's a really important thing to remember when it comes to implementing your depth first traversal. You're going to have to check if your children exist before you add them to your stack. And now in the final iteration, we have the F node. We remove it from the stack. We add it to our list of values. F has no children. And so I finish this iteration, and now my stack is empty. And I would just exit, right? Once the stack is empty, I know that I must have traveled through the entire binary tree. So there we have it. And we do get the correct output over here. So just by using a stack and just obeying the rules of the stack, that is, we push to the top and remove from the top, we will get the correct order. Important thing to remember is you should add your values into your values list whenever something leaves the stack. That being said, what can we say about the time and space complexity of this algorithm? Well, it's actually pretty straightforward. Let's say we define n as the number of nodes in this binary tree. Then we can say that the time complexity of this is O of n. And why do I say that? Well, we're just going to add every node eventually to our stack, and that node's also going to leave the stack exactly once. So it's not like we're double visiting any of the nodes, so I'm guaranteed to just run in O of n steps. In a similar way, we can say that the space complexity is O of n. The only thing we stored was really the stack, which is a linear data structure. And we know that we're not going to put ever more than n things on the stack. So overall, we have a linear time and space solution.
All right. So while root how do I set a condition to move forward? We start with the root and we end at what time? We end when the stack is empty? Do we push the root to the stack? And then while stack is not empty? I mean, in our drawing, we always have a value. Yeah. So let's see. Stack.push or stack.append roots. And we say while stack length of the stack is not equal to 0. Then we check the left node and the right node. Or we append first the right and then the left. We say stack dot append the right root dot right and stack dot append root dot left. So we add the left and the right to the root. Then we're saying add the right. Let me see. To the root. And we want to, or before we append, we want to remove stack.pop. So we want current is equal to stack.pop. We want to pop the value first, and we want to do something with that value. We want to say current dot value, or let's just say node dot value, node dot val. So we have the node, and we want to say this, we want to append to the values. Values dot append node dot val. We append the value, and then the next thing we want to do is make sure we set the node, it's not new root, it's node dot right, node dot left. We put it in this order, and then we're going to loop around. We're going to pop the left. So put this is in here. We pop it, set the value, or append the value, and then right first, left second. Pop this in here, append the value, right first, left second. Pop this in here, append the value, right first. But we need to check if it's not null. So we need to say if the current node, if node, then we stack, then we put the stack. So if we pass nulls, then we don't append. Is that it? No. If node, we want to, once we get to D, we pass, maybe just check if node dot right and node dot left. There's a better way to do this. Node dot right. If node dot right, no. I don't know. I'm gonna say if node dot right, then that. And if node dot left, then that. And if they're not true, then they just get skipped, and you go and you pop the next value. And at the end of the thing, we just return the values. To fail. None type has no object val. None type has no object val. How do we append a node? How did we append a none? should we just do? If node, then append root, something like that. No. If root, then append it. There we go. Let's see.
Hey programmers, Alvin here. Right now I want to walk through a Python solution for this depth first values problem. And so we'll jump right in over here.
The recursive, yeah. Let's see if I can do recursive. So this is iterative. And then let's see. Recursive. We're doing something different. I want to say the base case is if root so value is equal to this, and if root so that's iterative, and then recursive we would go like down. We'd have to append this to the values array. Like we'd have to define DFS. Root an empty array. Root and values, maybe. DFS root. Let's go node root and empty list. So we do that. We don't need to return anything, we just need to append. So we say if null, if node if not node, then we want to don't want to do anything, just want to return. Else we want to start out with the root. We want to append to values. We want values dot append node dot value. And then we go down to the left and then down to the right. So node DFS node dot left and the values array DFS node dot right. What do we do with the values? We just add them? Yeah,
But we'll jump right in over here. We know in this problem what we want to do is write a function that returns a list containing all the values in, of course, a depth first order. We mentioned that we can solve this one using a stack, and we'll start with the iterative version, right? So I'm going to create my stack. I'll just use a Python list. I think that's the most straightforward way to accomplish this. And I'm going to begin that stack with just the root value inside, right? So my stack is going to store instances of node, that's its elements. Now I can begin my main Python loop, so I can just check while my stack is not empty. So if you're familiar with some Python, you can just check while stack. It is the case that an empty collection type, so like an empty list, would be falsy. A list that contains at least one element would be truthy. So while my stack has some stuff, I'm able to run this while loop. Now when it comes to a single iteration of our algorithm, what I want to do is just remove the top of my stack. So I can do stack.pop, and that removes the last element of an array or a list. It also returns it to me. So I'll call that my current. Nice. And then from there, I can do a few different things with this current. For now, I think I'll just go ahead and print out this current value. So I'm not going to try to put it in a resulting list right now. I'll just kind of debug it as I go. And I know after I consider my current node and its value, I need to look at this node's children, right? So it's left child and right child. So I'm going to go ahead and do, I don't know, a current.left, and I'm going to push that into my stack. So I'll say stack.push current left, and I'll make it symmetric for current right. However, what I have to be aware of here is it could be the case that maybe this left child does not exist or the right child doesn't exist. If you look at some of the inputs here, if I look at, let's say the C node, let's say that the C node is my current. That means when I do current.left, that value is actually null, right? Or the none value. And so I don't want to put none into my stack. So I'm going to need to guard with an if statement. In other words, I only want to push the left child if I actually have that left child. So I'll check if current.left is not none. Right, so if it's not none, then I'll push it. And likewise for the right-hand side, if current.right is not none, then I'll also push it. Cool, so it's looking pretty good. I think at this point, that should be our kind of base code for our depth first, at least printing it out. So let's go ahead and just steal some of these manual test cases. Then we can run the automated ones in a little bit. So I'm just going to copy the snippet. We should be able to at least print some of these correct values. Cool, so I'm just writing this tree manually, and I'll bring in the class definition. I'll just run this. If you hit run, this will actually execute the file as is without running any of the automatic test cases. So here I'm getting an error. List has no attribute push because that's a JavaScript thing. So of course here I mean the append, right? So now I'll give that a run once again. And someone's going to be off. Here I get ACF BED, which is kind of not what we expect. We mentioned that a depth first traversal would be like ABD ECF. And what you'll notice is we actually technically still have a type of depth first traversal. except we're printing out the right-hand side before the left-hand side. So right now our implementation favors the right-hand side. So we'll travel to the right and then to the left. If you want to actually adjust that, it's just a matter of the order that you push the children. Based on how I have it implemented right now, it looks like I push the left child followed by the right child. So if I push the left and then the right, that means that the right child's going to end up on the top of the stack for the next iteration. And if the right's on top of the stack, that means I favor the right-hand side first. So if you actually flip the order of these, if you push right then left, then your left-hand side is going to be traveled to first. So I'll just adjust this. I'll run it again. And now I should get the correct print order of ABD ECF. ABD ECF. Awesome. So that's looking pretty good. And now I'm actually ready to probably add in the correct return value. So they mentioned that, hey, you need to return a list containing those values. So maybe starting at the top, I'll create that empty list. And as I visit nodes, that is, as I pop them, instead of printing them out, I'll just go ahead and append them to my value. So values.append current val. And then after my while loop, when my while loop is empty, or my stack is empty, the while loop will exit, and I can just return the entire values. Nice. So I'll run the test cases for this. We're missing one scenario, but we'll just see it fail. We'll fix it. So it looks like I'm getting none type object has no attribute val on test case 04. So if I look at that fourth test case, right bottom over here, it looks like they call the function and they pass in none, right? They pass in none, basically representing like the empty tree. What happens when I give you an empty tree? Well, what you should do is return an empty list. If you look at our code, we're actually going to put none into our stack, which is already suspicious because we should be putting just instances of node. And so this while loop is going to be true because I have an array or a list containing at least one element. And then when I pop, I'm popping none as my current, and then later on I say none.val, which would throw an error exactly on line 12. So you're going to have to guard against this like empty tree scenario manually. So I would just check up front, hey, if your root itself is none, then you can just automatically return an empty array. And I think with that, that should satisfy that edge case. So we'll run all these test cases once again, and I believe that will be our nice solution for this depth first values problem. Cool. So here's our nice iterative rendition. Let's also solve this one recursively, right? Because I know if we're using like a pretty explicit stack data structure for our depth first print or depth first values function, then I can also implement this recursively because any recursive code that we write uses the call stack under the hood. And that just happens automatically by your programming language. So if you want to write another version of this, here's how it might look. So I'll start by just stubbing out this function. So we'll say define depth first values, taking in the root of our tree. And like before, I need to kind of guard up top, which really takes the form of a base case. So if I'm going to solve this recursively, I need a base case about the simplest form of our input. Here your input's like a binary tree, right? So what's the smallest tree you could be given? Well, the smallest tree is really the empty tree. So it's not going to be about a tree of just one node. I can think of something smaller than that, right? The tree with 0 nodes. So pretty explicitly here, hey, if my root is none, so if I have an empty tree, then I could just return all of its values, which would be an empty array, right? So just return an empty array. Nice. And that's going to be really nice because it's consistent with the type of our return, right? They ask you for a list back. An empty list is still a list. Cool.
Okay, so you do if, instead of doing this, you can just do if root is none. If not root, then return empty array.
And so I know I'm going to have to make recursive calls here because I'm solving this recursively. So that means I call the same function, and I have to pass in different subtrees. So I can pass in my left subtree and also my right subtree. And here's how I'm able to like
root dot left and root dot right. Depth first values.
like quickly write recursive code, I kind of take the recursive leap of faith, I call it. So when I make this call, I think about what type it returns back to me. It's going to return back a list, right? A list of all the values in that left subtree. So I'll save that to a variable. I'll say maybe my left values. And this call over here gives me all of the values in the right subtree in another list. So I'll call that my right values. So I'll say, oops, just right values. Cool. So I have these two lists, and now I have to think about how I can combine those two lists to find my answer because I am like the root. So imagine that I was stepping through this example. So root would be the A node, and when I make the call to depth first values of root left is the B node. And technically what this result should just magically give back by the power of recursion, it should be a list containing all the values in that subtree, which would just be B, D, E in that order, right? So I'm going to assume I get correct information from this recursive call, right? So I get the values B, D, E. In the same way, if root is A, that means root.right is the C node. And when I make this recursive call, that would give me all the values in the entire right subtree. So that must give me back CF in that order. And now I kind of just have to answer the question, how can I take these two subarrays, combine it with myself because I'm the root, and that would be my entire answer? Well, it looks like I just need to combine these arrays, right? I just take myself A, follow it with all of these elements, and then follow that with all of these elements. So simply put, I can just return in line here. I'll return a new array, and what I'll do is take myself, so root val, and I can unpack or splat all the elements of my left values array. Also my right values array, so right values. So this is just going to unpack the array, basically just concatenating them all together over here. Awesome. So maybe you're unfamiliar with this like splat syntax in Python, so maybe I'll just demo that. So super quick aside, and
Actual was nothing.
promise I will run the code. So let's say I had some, we'll say people. We have some different people here. We'll say we got Jeff, we got Tommy, we got Rose.
I'm only human, and I've been damn. Some work, okay. So we do.
Of my left values array. In the same way, if root is A, that means root.right is the C node. And when I make this recursive call, that would give me all the values in the entire right subtree. So that must give me back CF in that order. And now I kind of just have to answer the question, how can I take these two subarrays, combine it with myself because I'm the root, and that would be my entire answer? Well, it looks like I just need to combine these arrays, right? I just take myself A, follow it with all of these elements, and then follow that with all of these elements. So simply put, I can just return in line here. I'll return a new array, and what I'll do is take myself, so root val, and I can unpack or splat all the elements of my left values array. Also my right values array, so right values. So this is just going to unpack the array, basically just concatenating them all together over here. Awesome. So maybe you're unfamiliar with this like splat syntax in Python, so maybe I'll just demo that. So super quick aside, and I promise I will run the code. So let's say I had some, we'll say people. We have some different people here. We'll say we got Jeff, we got Tommy, we got Rose, and let's say we had, I don't know, new people. And I'll just show you this pattern. So I can create a new array. So whenever I use square brackets, I get a new list in Python, right? And I'll throw down as the first element myself, Alvin, and then I'll spread out or splat all of the elements of the people list. And then afterwards, I can put, I don't know, some arbitrary elements. So we'll put in Brian, and we'll also put in Raj, and we'll go ahead and just print out new people. So the syntax I'm trying to reveal to us right now is what happens when we use the splat operator. Imagine we just take the people list and just, took out the square brackets around it, giving us just comma separated things, right? So I'll just run this as a script so you can see how.
Smooth operator. You can't do that. Yeah. You're spreading it. Star spreads it.
How that works. And when I print out new people, I should get Alvin, Jeff, Tommy, Rose, Brian, and Raj. So I kind of just took that
like
list and spread it out over here. Nice. So that's all we're doing. And now I think we're ready to run all these test cases. Cool. And there we have our recursive solution for depth first values. So maybe you're not a fan of this splat operator when it comes to like combining arrays. You're going to see me use that a lot. But, what you can also do is maybe just use the classic plus operator to concat. So you can say left values plus right values like that. But you need to be sure that you put this in a list as well, because you can only concatenate lists. So technically, this has to be its own list first for you to complete this concatenation. So that should actually work as well. It's really up to you.
Wait.
But no matter where you go and implement that line, I recommend you put this in a list as well. Because
how come that didn't work for me? That's what I tried also. And it didn't work. It said no. What? What was I doing before that? No. I don't know, man. Yeah, that's weird. I was doing something else, I guess. Right. Anyway, spread operator we're adding. Okay. Cool.